So today we have Amanda Forward she's a mathematician in the Pacific Northwest National Lab, and she's working on everything related with scientific machine learning, with limited data, physics-informed neural network, and so on and so forth. I don't want to talk too much about it, so welcome, and the floor is yours.
Thank you. So I want to acknowledge this is work done with many collaborators at PNNL. A lot of it is a joint grant with Brown University and at Columbia, and several interns that we've worked with over the last couple of years. I'm going to talk about today some of the issues with training physics-informed neural networks and some of the approaches we have taken to recover robust training when networks don't train well. I want to acknowledge that this is a really, really big field. There's a lot of people working on improving training of physics-informed neural networks, and a lot of different techniques have been developed. One of the really nice things is what I'll talk about today can be used in conjunction with those techniques that are coming out. So the work on optimizers in the last couple months, you could use the better optimizers that have been developed on top of what we're doing. Adaptive weighting schemes can be used on top of what we're doing. So for this talk, I'm going to focus on vanilla pins, vanilla depot nets, so we can look at how the techniques that we've developed work, but know that you can apply them with all the other methods. So physics-informed neural network uses physics instead of data to train a neural network. So what this is going to look like is the input to our network is the variables that are input to our differential equation, so things like space and time, and the output is the solution to a differential equation. And then we can use automatic differentiation to take derivatives of the output with respect to the input. So we can build up a loss function that has terms for how well you satisfy initial conditions, boundary conditions, and then the residual, that's how well you satisfy the physics. So all of these are going to be mean squared errors. How we'll pick a set of points on where the initial condition is. So that's how well you satisfy the initial condition. Same thing with the boundary conditions. And then for the residual term, we pick a bunch of points on the interior of the domain and use automatic differentiation to evaluate the equation at each of those points and use that to calculate the mean squared error for how we satisfy the physics. And ideally, if you minimize all of these terms simultaneously in your training, you now have a surrogate for your solution to this differential equation. So here's an example of how it works. This is a pendulum. So we split the pendulum into two first-order differential equations. We call those variables S1 and S2. You can think of those as the position and velocity of your pendulum, so it's moving back and forth. We're going to train a neural network. So our input is time, our output is S1 and S2. My network's actually bigger than this, but it wouldn't fit on the slide. Go back. And then we pick a bunch of collocation points. Those are the points on the interior of the domain where we're going to check if you satisfy the physics. We would pick them denser. We're going to pick them randomly at every iteration because that's been shown to improve the training while also being very inexpensive to compute those points. And we train our network and we get the solution that's in blue on top of my exact solution in black. So I now have the solution to a pendulum for time 0 to 4. So great. The problem is if I extend my time and instead of training from 0 to 4, I'm now training from 0 to 15. My pin solution now is pretty awful. So it gets stuck at 0, 0. So if you think about a pendulum, there's a fixed point at 0, 0. That's the stable fixed point. There's an unstable fixed point up here at the top. And it's been shown for dynamical systems that pins get stuck at fixed points. Once you're at that fixed point, it's really hard to bump away from the fixed point. And there are methods that have been developed. My concern is that this is a really simple equation. This should be really easy to train for if we're going to use pins for actual applications. And we're really struggling. So I want to be able to train a pin for a pendulum. And then from there, we can go to more complicated. So we'll talk about some ways that we've been able to improve this training. And at the end of the day, I'm not even really interested in training pins because pins map one input to one output. They're neural networks, they're function approximators. So for physics-informed training, that means you're mapping one initial condition to one solution. If you think in terms of numerical methods, you've now replaced one solve of your numerical method. But if you change your initial condition, you have to retrain, just like you'd have to rerun your numerical solver. What I'm interested in training is operator networks. So operator networks are operator approximators instead of function approximators. So they map a space of inputs to a space of outputs. For physics-informed DeepONet, specifically, that's going to map the space of initial conditions to the space of solutions. So now when you change your initial condition, you can just evaluate your DeepONet again. You don't have to retrain. So basically, you've replaced your numerical solver entirely. These are much more powerful, but they're also much more difficult to train. So in cases where pins fail to train, physics-informed DeepONets don't have a chance. So what we're really interested in is working on DeepONets. But I'm going to show a lot of examples with pins. And the reason for that is pins are much smaller, they're faster to train. And then once we develop an intuition with pins, we can transfer it to DeepONets and all of that knowledge transfers over. But it's easier to understand what's going on with the pin. So DeepONet consists of two neural networks, a branch network and a trunk network. These were developed out of George Kranjoudakis' group at Brown. The input to the branch network is your dependent variables. So for physics-informed training, that's going to be the initial condition. The input to the trunk network is, again, those space and time variables. We train all of these networks simultaneously, combine them at the end to get an approximator of your operator. DeepONets can be really difficult to train, but something that's been shown is this slightly modified architecture, we call these modified DeepONets, actually trains better by about an order of magnitude than a standard DeepONet. So this adds two encoder layers, and then the encoder layers are combined with every hidden layer of the branch and trunk network. Those increase expressivity of the network because instead of having to combine everything at the end in the dot product, we're combining them at every hidden layer. So anytime I say DeepONet, I'm actually training a modified DeepONet because they've been much more robust across our tests. So we think it's better to just start with a modified DeepONet. Okay, so a couple of years ago, we had this problem with ice sheet. So we wanted to do uncertainty quantification of the ice sheet velocities with respect to the basal friction field. So ice sheets are on land. So you have your land, you have your ice sheet on top. And the movement of the ice sheet is going to depend on the friction between the ice sheet and the substrate underneath. But if you think about an ice sheet, the friction varies in space, but it's going to be really hard to measure. Like you can't measure through your ice sheet to get that friction field. There are inverse, to solve an inverse problem, it's really expensive. You can try and approximate that friction field. But what we wanted to do was generate tons of friction fields and understand how the ice sheet velocity would change with all of these different frictions. We have this toy model called the Halford dome. This is the ice sheet height. So you can see it's a dome ice sheet. We generated a bunch of basal friction fields, and then we have a finite element code that gives us the ice sheet velocities given an input basal friction field and height. These are after 50 years. We generated about 200 of these, but we wanted to do thousands. And so what we wanted was to train a DeepONet to take as input a basal friction field and give us the ice sheet velocities. And finite element code works well, but it takes several minutes to run for every basal friction field. So if we can use a DeepONet where we can just do one fast evaluation of our network, we'll save significant computational time with all friction fields. So we stuck this into a DeepONet, we tried to train it, and it kept crashing because the memory needs for this really large data set were too large. It was too computationally intensive to train. So we generated a second data set. This one's on a 15 by 15 mesh. So you can see, like, obviously it's less accurate. Obviously we don't capture all of the fine scale features that we might want to capture, but it does a kind of decent job. We're going to call this our low fidelity data, and we're going to try and use as much low fidelity data as we can. And our 41 by 41 data is going to be our high fidelity data. So we want to use as much low fidelity data, as little high fidelity data as we can, but get the accuracy as if we used all high fidelity data to train. I will say that while I went down this multi-fidelity path, my colleague Kai Chi improved our standard DeepONet code to the point where we were able to train just with single fidelity data. And we actually have a hybrid DeepONet finite element code for ice sheet modeling now. That replaces the most expensive solve in the finite element code with a DeepONet surrogate. So we keep the same accuracy as running the entire finite element model without the surrogate, but we use just 20% of the computational time. So as an outcome of this project, we developed a really specific multi-fidelity framework we're going to use throughout this talk. So 3 blocks. One is a low fidelity subnet. That's going to be a surrogate model for your low fidelity data. The output of this low fidelity subnet is fed into a nonlinear and linear subnet. So the nonlinear and linear outputs are added together to become a surrogate for your high fidelity data. The linear subnet learns the linear correlation between the low fidelity output and the high fidelity data. And then the nonlinear subnet will be a nonlinear correlation, hopefully a small correction. Why do we have this really specific setup? For scientific data, we expect the low fidelity and high fidelity data to be strongly correlated. So we're not talking about images of cats and dogs, we're talking about different meshes, different numerical models. Maybe you have a low order model. So we expect the linear correlation to be able to capture the bulk of this correlation. But it's really easy to train a linear model, like it's AX plus B. So we only need a small amount of data to learn that linear correlation. And then this nonlinear correlation is going to be really small, so we can capture it again with a small network. That reduces the computational time and for training, and it also reduces the amount of high fidelity data we need. Each of these blocks can be whatever network architecture you want, or you could use, particularly for the low fidelity subnet, a lot of times we have a fast low order numerical solver, so we can replace this low fidelity subnet entirely and just use our numerical solver there, and I'll show some later on where we do that. For the first part of my talk, I'll use DeepONets for all 3 blocks, but then we'll explore some other architectures later on. Something I want to really point out here is that we do not need nested data. This is something that comes up a lot in the multi-fidelity community. Some multi-fidelity architectures need high fidelity, low fidelity pairs with the same input. So what that means is you have to be able to generate high fidelity data with the same input parameters as your low fidelity data. Or sometimes you need like your low fidelity data to be a subset of your high fidelity data. So the mesh, if you're doing numerical data, has to be like a coarsening of your high fidelity mesh. We don't need that. So our low fidelity and high fidelity data can be distinct. They can be on completely different meshes. If we think about physics-informed training with initial conditions, we can have completely different sets of initial conditions we're going to train the low and high fidelity data with. This is really important when you're looking at real data, experimental data, or even simulation data. It's not always possible to get these nested data sets or pairs of data. So removing that restriction is makes your method much more applicable. So this is what it looks like with DeepONets. What's nice is you can apply physics or you can use data. So here I have an example. We're going to do data-informed training for our low fidelity and then physics-informed training for our high fidelity, so using no high fidelity data. You can also switch that. Maybe you have a low-order physics model, but some high fidelity data, whatever makes sense for your problem. Our loss function looks complicated. Really, it's data-informed losses for high fidelity and low fidelity data, have it available, physics-informed loss, and then 2 penalty terms. So these penalty terms penalize the weights and biases of the nonlinear network and the low fidelity network. The penalty on the nonlinear network is to make sure that nonlinear correlation is small because we want to learn the maximum linear correlation. Penalty on the low fidelity network is because the low fidelity data is less accurate, it's likely noisy. We don't want to overfit to our noisy low fidelity data. And this is what it looks like with the ice sheets to give a more tangible example. The input to the branch net is the basal friction field and height. So for low fidelity, it is on a coarse mesh. Our low fidelity network is going to give us a low fidelity velocity field. The output of the velocity of the low fidelity network are fed into the nonlinear and linear subnets. So we basically append that low fidelity velocity field to the branch net for the nonlinear subnet. And in the end, what we get is a high fidelity prediction of the ice sheet velocities. To show a really simple example, this is a jump function. And the reason I like this example is when I'm talking about low fidelity data, I don't mean always data on a coarse mesh. We just mean less accurate data. So here our low fidelity data is are these orange dots. And you can see there's a lot of them, but they're really inaccurate. For high fidelity data, these blue dots up here, the exact solution is this blue. So if you try to train a DeepONet for a jump function with only 5 points, you get this blue line. Obviously, it doesn't know that jump is there. But when we train everything simultaneously, you get this black line that's on top of the blue line. It's able to capture the jump because it's getting that information from the low fidelity. And again, this is an operator. As we're training the DeepONet. So actually it's 2 input variables, parameter A, which is from 10 to 14. This is a standard benchmark for multi-fidelity training. That's why A is from 10 to 14. And then also X. So here I have two plots for two different values of A. And you can see in both cases, the single fidelity prediction, if you only use that high fidelity data, is pretty awful, but the multi-fidelity prediction is able to get that jump. What's cool about this setup is we can write down the linear correlation we learned. So the exact linear correlation should be 2 times the low fidelity minus 20x plus 20. This is what I learned, which is pretty close to that. Because of how DeepONets are set up, we have to actually learn a bilinear correlation. So there is this small bilinear term, but it is a pretty small. And you can play with this depending on how you weight the terms in the loss function. If we look at the errors, again, I said the predictions are a function of A and X. So our single fidelity errors go up to almost 20, and they're not capturing that jump at all. In the multi-fidelity predictions, the errors for our high fidelity predictions are really just concentrated right at that jump. And the reason for that is we don't perfectly resolve the jump in our low fidelity. So it's a little bit smeared out. But you can see our low fidelity error correlates really strongly with our high fidelity error. So if I added more low fidelity points to be able to resolve that jump better, we'd be able to reduce our high fidelity error. So it gives us a way to add low fidelity data to reduce the error in our high fidelity predictions. And we can do more complex correlations. It doesn't just have to be linear. This one is not a linear correlation, but we're able to do the same thing where we have inaccurate but lots of low fidelity data, small amount of high fidelity data, and our multi-fidelity prediction agrees much better with the exact solution than training a single fidelity EtherNet. And again, if we look at the errors, the multi-fidelity, high fidelity error correlates really strongly with multi-fidelity, low fidelity error. So adding some low fidelity data points up in here would reduce our high fidelity error. Okay, I'm going to go back to my ice sheets. Again, this is our setup. Okay, so what happens when we train this with the ice sheets? If we look at the single fidelity training, if we have 10 data sets for our high fidelity data, we get an error of 16%. We need to go to 50 high fidelity data sets to get an error that is small enough for us to use for the application we were working on for this project. In the multi-fidelity training, we use just 10 high fidelity data sets with 100 low fidelity data sets. Those low fidelity data sets are small to store and inexpensive to compute, so I don't mind having a lot of them. But we get a smaller error than using 50 high fidelity data sets on their own. So basically, we reduce the amount of high fidelity data we need by a factor of 5, which is really great for us. And if we look at the outputs from training, we have our single fidelity training with 50 high fidelity data sets and our multi-fidelity training with just 10. Our velocity fields look really similar and our error plots look really similar. I actually think the multi-fidelity one is a little bit better. It's a little bit less noisy in these areas that affect zero velocity. So we've been able to reduce the amount of high fidelity data and the time to generate that data significantly. And we can do more physical ice sheets as well. This is the Humboldt Glacier in Greenland. And I like this example because we're actually going to use the same mesh for our low and high fidelity data, but we're going to use 2 different numerical methods to generate the data. So our low fidelity data is generated with the monolayer higher order model. So that's an approximation. So ice sheets are governed by Stokes flow, and then you can make approximations basically assuming the velocity through the ice sheet is uniform. And then our high fidelity data will be generated with the shallow shelf approximation. So that's a higher order approximation of Stokes flow. And so we don't have meshing the ice sheets is actually really computationally expensive. So we don't have to generate a new mesh, but we have faster code to generate our low fidelity data. And when we look at the output, here is our exact solution for the velocity after 100 years for this particular basal friction field. If you look at single fidelity training where we only use that high fidelity data, the magnitudes of the velocity are really big. They're very unphysical, but the multi-fidelity does much better. The multi-fidelity is able to capture the features of the exact solution. And of course, that comes across in the error as well. So the errors for the multi-fidelity training are about an order of magnitude lower than the errors for the single fidelity. So here we've reduced the computational cost to generate our data. But I said we can also do physics-informed training. So everything I showed before was data-informed. Now we're going to say, what if we don't have high fidelity data? We can't generate it, or maybe it's really expensive to put together a numerical model. So we look at Berger's equation. I'll do low fidelity simulation. And then instead of high fidelity data, we're going to enforce physics. We'll do a physics informed DeepONet for the high fidelity training. The reason we picked this example is it's a really canonical example for physics informed DeepONets for a case where physics informed DeepONets do not perform very well. So if we look at physics only training for a DeepONet, the important parameter here is the viscosity. So we start with high viscosity on the left and move to small viscosity on the right. Physics informed DeepONet with this small viscosity has an error of about 24%. Obviously, that's not a model we want to use. There are methods to reduce that error. I'll talk about them a little bit further on, but when I was doing this work, it did not exist. Okay, so the data only training. This is kind of an interesting example because we have really great numerical solvers for Burger's equation. And I took an entire class in grad school on numerical solvers for Burger's equations. We're able to generate really accurate data. Even on, I used a really coarse mesh here because I wanted it to be low fidelity. So in these three columns, we have 1,000 low fidelity data sets that we generated. In this last column, we only have 200. So that's looking at a case where you can't generate a lot of data. So the errors are smaller than the physics informed training. The data only training actually does pretty well, as long as you have enough data. When you go down to this 200 case data set, there's only, the error basically doubles. So the data only training does well if you have a lot of data. DeepONets are data hungry. We also wanted to say, okay, well, for Burger's equation, we have really great numerical solvers, but what if we didn't have a really good numerical solver? So we simulated this case by adding noise to our data, so we could control the noise level. And we see the same thing. So the errors increase significantly from the data only training. They're okay until you reach this case where you have very little data. And then our data only training with noise errors increase significantly again. So in the multi-fidelity training, across the board, we do better than physics only training. So in this case, where physics informed DeepONet struggled to train, adding even a little bit of low fidelity data does help the network to train. And what's really interesting is even if that data is noisy, the errors don't increase substantially. So adding the physics is able to accommodate the noise in the data and correct for it. And in our worst case scenario where we have noisy data, we have a little bit of data, we've brought the error down from 24, 26% to 10% by using multi-fidelity training. And this is the output for one sample initial condition. Here's our exact solution. We have data only physics only and multi-fidelity training. And if you look at the data only error, it's kind of noisy. That's because we're in our worst case scenario, so small amount of data with noise. The physics only fails to capture the gradients that form the shock in Burger's equation. It actually finds it kind of the wrong place a lot of the time. So the multi-fidelity errors are smaller. And if we look at the solution over time, it does look better. Any questions on the multi-fidelity before I move on to the next topic? Okay, so everything I showed so far had some data that we could use for our low fidelity or high fidelity. But we had a question, what if we don't have data available? What can we do? So I said that physics informed neural networks and DeepONets can be difficult to train. And so what we get, this is the wave equation. This is a pen trained for the wave equation. This is not a good solution to the wave equation for this set of parameters. But if you kind of squint, it kind of looks like the right equation. So we're going to treat the output of this pen as our low fidelity data now. And we're going to train a multi-fidelity pen. So this gets as input this previous solution and learns a correction to it. And now we're getting something that looks closer to the wave equation. And we can do it again and again and again. And you can think of this like progressively learning corrections to your previously trained model until down here we get a solution that has the accuracy we want. I originally called these bootstrapping pins because I kind of think of like bootstrapping the solution. We're going to just keep learning a correction until we get the right solution, but it turns out someone took that name. So now they're called stacking pins. But we've been able to use this with a lot of success. When we were doing this paper, so originally we just added the linear and nonlinear outputs together. What we found for the stacking pins is it's actually better to add a trainable parameter alpha and take a linear combination of the linear and nonlinear outputs. And then we penalize alpha to the fourth inner loss function. The reason for that is we want alpha small, but not too small. If alpha is large, you only learn the nonlinear correlation and not the linear correlation. And if alpha is too small, you don't learn a nonlinear correction. The nonlinear part goes to zero, so you only learn a linear correlation. So you want to learn the maximum linear correlation, but you want some flexibility to learn a nonlinear correction. So we'll go back to the pendulum. I trained a pin 10 times for the pendulum to try and get the best set of hyperparameters I could. You can see in every single case, it decays to that fixed point. Pretty much anytime you train a pin for a pendulum, it's getting stuck in that point. And this is what we get with the stacking. So in the beginning, it doesn't look so great, but we're able to progressively learn those corrections until we're reaching the accuracy that we want. So it's helpful to look, this is the stacking step or iteration on the x-axis and the relative L2 error. So they all start with this large relative L2 error, and then the error decreases to a pretty relatively constant minimum value. These networks are really small, so they do saturate, but you can increase the size of the network if you want it to keep training once it starts to saturate. And they all kind of follow their own trajectories, but they all do get there eventually. So this is 10 different initializations. So a case that's really hard for pins to learn is multi-scale features, really fine scale features, oscillations, those types of things. So we have this toy model that has two different frequencies of oscillations. This is a case where you can train a pin for this equation, but it has to be a really big network. So I trained 4 different network sizes. The way to read this is it's 3 hidden layers with 32 neurons each. To reach our exact solution, and you can see it really in the inset, we need this big network that's 5 hidden layers with 64 neurons each, which I know is not big in the grand scheme of network sizes, but in the grand scheme of trying to solve such a simple equation, that's a pretty big network. This is what you get with the stacking. So after 3 stacking steps, we've reached a lower error than our best case, our best trained pin that we were able to find. That's shown in the black line. And then what's nice is you can keep going. And so eventually the error does decrease even further. So we're able to get higher accuracy out than we were with a pin on its own. And we're able to do so with fewer trainable parameters. So with our network that had 4 hidden layers with 64 neurons each, our error was too large. So we needed 5 hidden layers with 64 neurons each. That's 17,000 in an error. The stacking pin has 5,000 trainable parameters to reach the same error. And even if we go down to 10 levels, so over here, we have a smaller error and we still have fewer trainable parameters. The reason this works is our nonlinear correction is small, so that network is small, and so we're able to train these very small networks sequentially. So you're basically, instead of training one big problem in parallel, you're training small problems. These are pins, these all train on my laptop. So, reducing from 17,000 trainable parameters to 11,000 is not that exciting a prospect. But when you move to DeepONets or when you move to larger applications, this can be a pretty substantial savings. It also can mean that you can train on a laptop instead of a GPU. One of the things we're really interested in at PNNL is edge computing. So how do I evaluate and train networks on very, very small devices? And in this case, reducing the number of trainable parameters, even if it takes longer on the wall clock to train, can mean we can train in cases where you couldn't train before. So we're excited about this and the applications that we can do now that we didn't have the computational resources to do. Again, this works also for the wave equation. I showed that at the beginning, and the wave equation actually introduces something interesting about the stacking network. So normally we keep the equation fixed at every stacking step, but what we've actually seen is that changing the equation can help. So the important parameter in the wave equation is the wave speed c. So here we're keeping c fixed, that's equals 2. This is my exact solution I'm trying to match as we have stacking steps. Increase in accuracy, moving down, and the error decreases, again, moving down. Here we're going to change the wave speeds. So it's easier to train a pin when your wave speed is smaller. So that's going to be c equals 1. So we'll start by training our first network in c equals 1. This trains really well. It's a much easier problem. Then we're going to increase speed, and we'll keep increasing it, like taking steps to get to the solution that we wanted, which is equal to. And so again, moving down, these are my exact solutions. These are my predicted solutions and my errors. So what we see when we look at the error at each iteration is, okay, if you keep the equation fixed at every step, the method does work. So that's this orange line c equals 2 at every step, it does converge. If we change the equation, we actually do better. So starting with the wrong equation, c equals 1, and then moving towards c equals 2, I have two different schedules in the blue and the green. These both reach a smaller relative L2 error faster than case 1. The reason for this is our method is built on learning correlations between the previously learned solution and the next solution. And so if your previous network is better trained, that correlation is going to be more robust. If your previous network is noisy and that correlation can't be learned robustly, you're going to struggle with training. So I actually suggest you start with an easier problem and move your way to a harder problem. And this has let us reach some regimes that we weren't able to reach before. So here we're going to go all the way down to c equals 4. So we start with c equals 1 and then move to c equals 2 and c equals 3, and we're able to keep taking steps to get to a desired solution. And of course, I said, we'll do it with pins first, but it does all work with DepoNet. So I'm going to go back to that hard problem, Berger's equation with small viscosity. That's where I said we had a 24% error. That's what this looks like. This is a 24% error in your prediction. So obviously my single fidelity solution in blue does not agree well with my exact solution in black. But we can feed that into a multi-fidelity DepoNet, train it again. And now we're getting this orange line that's a little bit closer to my exact solution. And we can iterate that and do it again. And now we're getting the green line. So now we're getting somewhere that's looking like our exact solution. And we can keep going. So in the end, we have this red line that's agreeing pretty well with our exact solution. When we were doing this work, the state of the art was training DepoNets with what's called the neural tangent kernel, or NTK. This is basically an adaptive weighting scheme for physics-informed DepoNets, and it reduces. So this is my 24% error up here. Using the neural tangent kernel reduces it to an 11% error. You might say, well, why don't we always use the neural tangent kernel? It also increases the computational time by a factor of 6. So if you don't need it, you don't use it. But this dotted line was the state of the art when I wrote this paper. So 11% error for this problem. By starting with a big viscosity and decreasing the viscosity at each step and using the neural tangent kernel, we get this blue line down here where we're able to cut the error in half. So by using the stacking, we're able to beat the state of the art for a physics-informed DepoNet pretty significantly. And then we thought, okay, well, that's great, but where else can we take this? And something we're interested in is domain decomposition. So we're going to use finite basis. So finite basis can use partition of unity functions. So I'm going to have 4 subdomains. I have 4 partition of unity functions. We train 4 networks, 1 in each subdomain. We weight the outputs by the partition of unity functions, and then we add them together to get a solution. And we can combine this with the stacking. So I start by training 1 network in the whole domain. Again, this is pendulum. This is not a good solution for pendulum, but we feed it into now 2 multi-fidelity networks. Each learns a solution. So this is the output. Each one has a partition of unity function. So we weight the outputs by their partition of unity functions, and then we add them together. And we can keep going. In this work, I'll do 1, 2, 4 subdomains. And each time now we're beginning to look pretty close to the solution for a pendulum. So this works really well for the pendulum, as I said before. Compared to what we did before with the stacking pins, the stacking FB pins, the domain decomposition version converges faster to a lower relative L2 error. And the same for this multi-scale problem. Again, so what we had before was the blue line. Now we have this yellow line, so we're converging faster to a smaller relative L2 error. So you could say, okay, great, but you're adding networks at each step. So here I added 1 network, but down here I added 2 networks. Of course, it's more accurate. But what we find is we still need fewer trainable parameters. So at this second level, we're reaching a smaller error than our final level of the stacking stacking pin. That's this point over here, but we have fewer trainable parameters. And again, that's because those networks are so small. And in the end, we're able to reach an even smaller error. So yes, this is significantly more trainable parameters, but if your goal is to get the most accurate solution out you can, maybe that's the trade-off you're willing to make. We have looked at multi-fidelity networks in a variety of applications. We have a paper on continual learning where you can, so in continual learning, you get new data sets and you need to learn a model that can model those new data sets and the old data set simultaneously without using the old data. And what we found is using multi-fidelity training can reduce forgetting. So you basically trade your previously trained model on the previous data sets as a low fidelity version of your current data, and you're able to reduce forgetting. We also have a paper on the conjugate kernel, which is a surrogate for the neural tangent kernel. It's a zero order approximation of the neural tangent kernel. So it has the same accuracy as the neural tangent kernel for many physics-informed DeepNet problems, but it only increases the computational time by a factor of 2 instead of a factor of 6. So you can get same performance, but much faster. But all of the questions I get on my work now are about Kolmogorov-Arnold networks. So I'm going to spend the rest of the time talking about cons. So neural networks, MLPs, use trainable weights and biases with fixed activation functions. Cons use trainable activation functions. So what you get is something that's kind of interpretable. So we always plot cons upside down. For some reason, that's just become the convention. So the inputs are down at the bottom. Our input is x and y. These are my trainable activation functions for some toy equation, and my output is at the top. The nodes here represent addition. So this paper came out about a year ago now, to a lot of conversation in the machine learning community. A lot of people like them. They are a newer technology, so they are harder to train right now in some cases. And one of the issues is it's really hard to train a big con. It's unclear if you need to because they can be more expressive with smaller networks. But if you really need to train a really big or deep neural network to model your problem, it's going to be hard to do that same problem with a con because it's hard to train a wide or deep con. So we developed FB cons, finite basis cons, to overcome that problem. So we're going to use the same domain decomposition technique we used before, where we have these partition infinity functions, have 4 subdomains here. We're going to train 4 cons simultaneously, weight them by their partition immunity functions, and then add them together to get a solution. And what this lets us do is train small networks instead of one big network. A question I get asked is, when should I use a con? And my answer for that is, if you have noisy data, cons seem to do really well. And the reason I think that is they are fitting polynomial splines. You can use other basis functions, but in the original version, they're fitting polynomial splines. So those splines are going to kind of smooth out noisy data. So this is a toy model with noisy data. My exact solution is in black. We're going to train a con and an FB con that has 4 subdomains for the same problem. So here's the output of the training. This con pretty small to get it to train well, but that means it's not able to capture these finer scale oscillations. You can see the green line doesn't agree very well. The FB con does much better. One of the interesting things about cons is you can do adaptive basically adaptive grid resolution while you're training. So you add more splines adaptively while you're training. The equivalent for that for a neural network would be like a way to make your network wider while you're training it, but we don't have technology to do that right now. But that's why you get these loss functions for cons where they can stagnate and then you refine the grid and they start training again, which is kind of a cool thing to play around with as someone coming from like a numerical methods math background. I like adaptive grid refinement. Our errors are down here, so you can see the FB con does much better than the con solution. But I think the interesting plot is on the right. This is looking at the relative noise that we added to our data set versus the relative error. So across the board, the FB con in blue does better than the con, but the errors don't increase significantly as we add that relative noise. And this is going up to 17% relative noise. So this is a pretty large data set, but what we're seeing is that the con is doing really well in the presence of this noisy data. So it might be a case where you want to use a con. We can also do it for physics-informed training. So this is the Helmholtz equation. I like it for domain decomposition because it has those finer scale features. If you try and train a con for this problem, it really struggles. So you can see this is not a well-trained con. The errors are really large. I have two FB-cons here with 4 and 16 subdomains. In both cases, they do much better than one subdomain up here, or one full domain. The errors are smaller. 16 does outperform 4. The boundary condition here should be 0, so we can look at the boundary condition and the error at the boundary. The con error is like really large, and then the error decreases as we add subdomains. We do have tutorials online through Neuromancer for our work with cons and for the stacking networks. So if you want to check those out, I'll have a QR code at the end, so you don't have to type this URL in, but you can play around with these examples and try out the FB cons and see how they train. And I'll end with the multi-fidelity con. So one of the things you hear about cons is they're interpretable. So you can do symbolic regression and kind of try and figure out what equations you're learning, but even just looking at the activation functions, we can learn something about our equations. So this is a little bit of a toy model. But our low fidelity equation here is 0.2y squared plus 0.1x cubed. X and y are positive for my domain, that's 0 to 1. And you can kind of see all my activation functions look kind of like, you know, cubic, quadratic polynomial. Much like our multi-fidelity setup before, we're now going to feed the output of our low fidelity model into a linear and nonlinear block. Our high fidelity equation is the low fidelity minus x minus y plus sine of 10x. So if we look at the linear correlation here, we learned something that's positively correlated with the low fidelity minus x, or minus x minus y. So you're able to interpret that linear correlation you're learning. Our nonlinear correlation is kind of harder to understand the activation functions, but you can see over here we're learning sine of 10x, and there's a little bit of an error here, but it is learning sine of 10x. And I mean, what I can say is these activation functions are kind of more wiggly. They have higher frequency oscillations because they're having to get to sine of 10x again. And then we add those together, so this is our final solution. Something that you could play around with the multi-fidelity cons is maybe you know a linear correlation is not going to capture the correlation between your low and high fidelity data because you know something about your measurement error. But you could say, okay, but I know it's quadratic. So instead of learning linear correlation there, I'm going to learn a quadratic correlation because at its base, what cons are doing are learning polynomial splines. So we learn a linear correlation just by forcing it to be a first degree polynomial. We could also force it to be, you know, a quadratic polynomial. Okay, this is the slide I showed before. The other question, I guess, is when should you not use a con? So this was my multi-fidelity DeepONet for the jump function. The important thing here is to look at the jump. It's resolved pretty well. When you do the same thing with a con, this is the low fidelity output, it's not able to resolve that jump as well. And the reason for that is it's, again, learning, this is cubic polynomial, so it has to put a cubic polynomial to a jump function. It's not going to be able to do that perfectly. The multi-fidelity version still trains. It still is better. If we look at this as a high fidelity output, we train only with the high fidelity data, we get this red line, so it's not capturing the jump at all. So the multi-fidelity con is better than a single fidelity con. I probably would use an MLP for this problem. If I knew there was a jump in my data, I would not. One of the interesting things that can come up with cons, and there's more details about this in our paper, is they can really struggle with sparse data, and you can get kind of, because if you think about fitting cubic polynomials to sparse data, they can kind of end up all over the place. So we had to add this weighting term that basically limits oscillations in our output. So you do slightly better when the weighting term is turned on. That's W plus 1 instead of W plus 1. But you know, you're able to capture the jump. It is learning multi-fidelity. And we do have a tutorial online for the multi-fidelity cons too. But I'm going to end after this example, talking about some other things to consider when you're doing multi-fidelity training. These are things something I see come up a lot when I am reviewing papers and reading papers and talking to people who do multi-fidelity work. And that's that you need to think about how you're generating your high fidelity data, and is it really a smart way to generate high fidelity data to reduce the computational cost. So we're going to look at flow past the cylinder. I love fluid dynamics, so a lot of my examples are fluid dynamics. We're going to go up to t equals 200 here, but I want to reduce the cost to generate my high fidelity data. So we have two different meshes, a low fidelity, high fidelity simulation. This is all my data. So I ran my low fidelity and my high fidelity data a really common way to generate a high fidelity data set is people say, we want sparse data. So we'll delete every other time step. The issue with this is I still have to run my high fidelity simulation all the way out. I didn't actually save any computational time. You maybe save time in training your model because your data set's smaller. You save memory for not having to store the whole data set, but you're not saving computational time. And most of the times when we're doing high fidelity or doing multi-fidelity training, it's because we do not have enough resources to generate our whole high fidelity data set that we need. What you want to do instead is this. We're here, I'm only going to have high fidelity data from 0 to 100. What this means is my network needs to do extrapolation. So to get the predictions out over here, we're going to have to do extrapolation in the high fidelity data space. Cons, MLPs, deep nets all struggle with extrapolation. This is a really common problem. But what was shown is by using this low fidelity data, we can do extrapolation fidelity time because you have that low fidelity to fall back on. So this is what it looks like. And my simulation at the top, multi-fidelity, single fidelity, that only gets the high fidelity data. They all do pretty well up to 100. And then we just hit 100 and my single fidelity is now awful. It can't extrapolate. So as the time increases, it gets worse and worse. The multi-fidelity is still going. So I'll play this video again so we can watch it, maybe. Okay, yeah, so they all do pretty well. The single fidelity is a little bit better than the multi-fidelity, up to 100. And then the multi-fidelity is able to keep going while the single fidelity fails. Something to note, so one of the questions I get is, is the network just learning to interpolate the low fidelity onto a high fidelity mesh? The reason I pick flow past a cylinder is there's this boundary layer around the cylinder that's not resolved in the low fidelity simulations very well. So if you just interpolate the low fidelity into high fidelity mesh, you get this blue line. So that's not very accurate. The multi-fidelity really is learning the correlation between the low and high fidelity data, and that gives us this black line. So once we hit t equals 100, the error does not increase substantially. If you just use the high fidelity data, it does a little bit better at the beginning, but then it does jumps as soon as you don't have data. I can't extrapolate, and the error increases substantially at the end. And if you keep running the simulation out, the error just continues to grow. So again, I said that this boundary layer is not resolved in the low fidelity simulation. It is in the high fidelity simulation. It's a little bit hard to see on the slide, but it's there. The single fidelity training and the multi-fidelity training both do capture this region. This is when there is data, so at t equals 25, and when there isn't data at t equals 100 or 200, you can see the single fidelity is now awful, but the multi-fidelity is able to keep going and it's able to capture these features. Okay, so that I'm happy to take questions. There's a QR code that has links to our tutorials and our papers if you want to test these methods out. And I'd like to acknowledge this project is part of a DOE Mimic Center funded by ASCR, Advanced Scientific Computing Research. So it's a collaboration with PNNL and with Brown University. So thank you.
You showed lots of the cons you pointed out the noise graph. And at this point in the noise, it seems like, I believe it's the epicons got slightly better as you increase the amount of noise. Yeah, the relative area drop.
I think some of this it also depends on the initialization of the network. So this is one initialization instead of averaging over multiple. So I think some of that is what you're seeing. I wouldn't pay attention to those slight variations, but I do think cons do really well with noisy data in general. They're able to kind of overcome. Yeah. Right. Yeah, so let me go back to, okay. So you can think of the trunk as learning the basis, and then the branch learns the coefficients in front of the basis. We are just training a neural network to come up with what that basis should be. And we do have a paper we just published looking at that basis. So you can plot the functions and see what you learn. It looks a lot like kind of what you would expect, like a Chebyshev polynomial basis. It's not exactly because it is learned from your data or your physics. But it does kind of approximate, oscillating functions with the number of zeros as increasing with the number of basis functions. How you better training of that basis significantly influences the accuracy of your results, which would make sense. And so there are methods now that separate the training of a branch and trunk. I don't know a lot about, I don't use them right now, but I would recommend looking at that if you really want to understand the basis functions and want more robust training of those basis functions. So you definitely can. I showed the figure here, but one of the things, so like if you do this for Berger's equation, when you get those shocks, you actually get basis functions that can capture the shocks. So they have like little discontinuities in them. And so you're not going to get, I guess you could try and come up with that on your own, but you probably will do better training for those types of cases to be able to capture that versus things where you have, like for smooth functions, you kind of pick your own basis and just train to branch network, and people do that. Yes.
Have you encountered where like this multi-ability learning model?
So you're saying adding in the low fidelity data can reduce the accuracy?
Yeah, like there's some like bias in the data that isn't high fidelity data where you train a network on high fidelity data that performs well, but if you try to include more data, that's the model on.
Yeah, so that's kind of what's happening here, where you can see that in the beginning, the high fidelity error is lower than the multi-fidelity, because we do have enough high fidelity data to train with. If you just use your high fidelity data, you're losing that bias from the low fidelity data. But we can't, like, you can't use only high fidelity data because it's not going to work at the end of the domain. So if you have enough high fidelity data to train well and you're happy with your model performance, I would not use multi-fidelity training. It's not always going to add something. But we're really interested in those cases where you cannot do high fidelity training. Yeah. Yeah, so the original con paper used B-splines with basically no constraint. Oh, yeah. Okay, the question is, for the cons, do we impose additional constraints on the splines? We do not, because I was matching the original paper. What has come out in the last year, and it feels like there's more papers every week, is that B-splines are maybe not the best basis to use for training cons. Different, like Chebyshev polynomials, are called Chebby cons, seem to do better. There's higher order ReLU cons. Basically, there's various versions of those basis functions that seem to train much better. I think we'll see a lot of work over the next couple of years on improved training for cons using either constraints on the basis functions or different spaces for those basis functions. Yeah, but everything we did, you can just swap out those architectures. So nothing I used, except for the linear network, assumes that you have all of it.
Hi, Amanda. Yeah, can you hear me?
I can hear you, and I'll repeat the question.
Oh, perfect. Yeah, so I'm Nick. Thank you so much for putting together this talk. It was really great. I just had one quick question. When you are training the networks with going from a parameter like in your PDE from sort of an easy regime to a harder regime by varying this parameter over and over again until you reach the regime that you care about. Are you also allowing that parameter to be an input into the network? So you're sort of able to stitch between these trainings, sort of like interpolating between that parameter? And if so, is that, or sorry, if not, is that something you've considered looking into?
Yeah, so it is not what we did in the stacking paper. So the question is, when we vary the equation in the stacking pen, do we use the input, like the parameter that's changing as an input to the network so we could interpolate between the different levels? It's not what we did in the stacking network, but we do have a lot of questions now about how to really capitalize on what we've done here and make it more robust, make it more applicable to other problems. It's not even clear always what the parameter you should vary is. So this is something that we are actively looking at now.
Awesome. Thank you so much.
Thank you again.
Thank you.